Welcome to lecture number 10. So, in last lecture I had mentioned that if time remains we will cover this conductivity in relation to band structure. So, now let me try to do it in this lecture, and then I will make some comments on conductivity of materials in this lecture. Remember, what did we see last time? In previous lecture we defined a quantity called effective mass, and we found it to be a strange quantity that it turned out to be somewhere, some places going to infinity. Of course, that is one feature, but more importantly, which I probably did not mention in the previous lecture, was in other places you would have noticed that effective mass was a negative quantity. This negative quantity is what we are going to look for and see, try to define what idea, we will try to give the idea of what an hole is, and that you have heard of in semiconductors. There you have heard of electrons and you have heard of holes. Remember, in metals we always talk of electrons, whereas the moment we move on to semiconductors we start introducing another term called holes, and commonly in school the way it is taught, it is said that holes are absence of electrons. Fair enough, but what precisely it means, that I am now about to explain to you in context of these band diagrams. When you start looking in conductivity in terms of band structure, that comes out naturally. So, what is that I am going to now talk about? Let us look at it again. Let us look at the band structure. Let us look at a hypothetical schematic of a band structure. We again plot our band structure just like we did for nearly free electrons. So, let us do that and let us look at what happens. I am going to plot 4 different bands. So, I am going to take this line E versus K curve. Here is E versus K diagram which I am plotting, and in that I am going to plot out here again up to in the first Brillouin zone only. So, I am marking the first Brillouin zone. This is K and this is energy, and here is K by 2 and minus K by 2 showing the Brillouin zone. Here is 0. So, that is the Brillouin zone. I am now going to draw 4 different bands, and remember, just like we did in nearly free electron, I am going to draw those bands right here. It is not important what the precise shape of the band structure is, what exactly the band structure is, but I am just for as a schematic I am going to put down 4 different bands whose shape and nature will be exactly like that we derived in a nearly free electron theory, like electronic penny model. So, let me draw that first. Now, those, let us draw it like this. Second band like this, and then again somewhere up to here, and then again somewhere up to somewhere, something like this. These are my 4 bands, let us say. What does that mean? That means these are allowed energies. That means up to here these are allowed energies. There is a gap in between. Then these are allowed energies. There is a gap in between. These are allowed energies right here. These are the allowed energies, and then there is a gap in between. So, you can keep seeing gaps in between, and then these are called bands. So, these are the energy bands right here, right here, right here, right here are the allowed energies. This corresponds to this point right here, and this is of course is right here. So, these are the bands, allowed values of energies, and band gap in between, energies which are not allowed for electrons. So, those are the band gaps. Okay. Now, what we are going to do is we are going to start placing electrons on these. So, in order to place electrons, let us choose 2 different colors. Let us say we choose red color for electrons. So, here is an electron, and I am going to place electron here. I am going to place electron here. I am going to place electron here, 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 and let us say here. I have placed all these electrons in here. So, what am I showing on these bands? There are case on these electron bands on the k states. In this particular band, let us call it band number 1. Let this be called as band number 1, but let us write it not Roman, but just band number 1. this is band number 2, this is band number 3, this is band number 4. So, 4, 3, 2 and 1. These are the 4 different bands, energy bands which we have. What I am showing you is in energy band 1 different K states, and all these K state electrons are completely filling it. That means band 1 is completely full of electrons, totally filled. Likewise, what I am going to do is I am going to fill up band number 2 also. So, I am going to fill up all the K states, I am going to fill up these electrons in there as well. Even this band number 2 is completely full. Band number 2 is completely full with electrons. I have put all the electrons in there. What about band number 3 and band number 4? Let us say band number 3 and band number 4 are completely empty. There are no electrons in band number. So, what I am showing you is band 1 and 2 are full of electrons, and 3 and 4 are empty. So, that is what the picture is. Now, let us say this is picture, let us say as 0 K, at 0 Kelvin, that is the temperature, and bands are completely full, and that is what the picture is. Now, suppose I go to room temperature. I go to room temperature, and in this case what happens, since there is some thermal energy, some electrons which are sitting right at the top of the band, right here, say this electron has the highest energy here, it is sitting at the top of the band, and these electrons which are sitting on the top of the band can now begin to jump. Suppose they begin to jump into the next higher band. So, this next higher band they jump. So, let us draw that picture also. So, if I draw with that picture, then I quickly draw identical picture like this, and this is the first Brillouin zone which I am drawing right here. So, E versus K diagram, again K by 2 and minus K by 2. If I draw this minus K by 2 and then I draw the same bands like this. These are again the 4 bands which I have. These are 4 bands which I have. In this case, now again what I do, I put all these electrons here. And what I have done is, what I am going to do is, I am going to cause 3 of these electrons to jump up there, because I am at room temperature now. And what I will do is, with the green pen, green dots, I am going to show here 3 states which have become empty. These electrons have jumped up in the band number 3, and now the band number 2 is partially empty. And this is the picture at room temperature, let us say at room temperature. At room temperature this has happened, some electrons have jumped up there. Now, suppose I apply electric field and ask how the conduction will happen. For that, let me draw another third picture also. Similarly, exactly similarly, let me draw the third picture. This is K by 2 minus K by 2, 0, and on top of that now I am imposing a electric field. I am applying electric field in, let us say, in K direction. So, if I do that, what will happen? Let us put the electrons again. Now, what I am going to do is, when I apply the electric field, let us say these electrons have drifted on one side. So, I am going to draw this as like this, and I am going to plot like this. This is when electric field is applied. Now, let us look at conductivity. What happens? Let us look at 0 k. So, let us look at this picture right here, which is shown here, and let us look at 0 k, what the conductivity will be. Let us look at electrons in each band and see what happens. We will start with band number 4 and band number 3. So, let us look at this 0 k, bands 3 and 4. Both are empty, hence cannot contribute to conduction. So, they cannot contribute to conduction. What that means is empty bands do not conduct. That is the conclusion. Clearly, if a band does not have electrons, how can it conduct? Those are energy states available, but if they are not occupied by electrons, electrons are not there, in that case we cannot have any conduction through those bands. So, band number 3 and 4 in 0 k, this picture right here at 0 k, therefore cannot conduct. In band number 3 right here and 4 cannot conduct. What about band number 1 and 2? So, let us look at bands 1 and 2 at 0 k. Bands 1 and 2, they are completely full. Which means if I apply electric field, which means if I apply a force called this force on an electron, then that should cause, remember, H should be dk dt, rate of change of momentum. That is what that means. In time, the k state should change. So much so, you will recall, then k state at some time tau should be equal to, that quantity should be equal to at 0 time whatever the state initially was. If I apply an electric field, in that case k tau should be equal to k 0 plus some quantity minus q E by h bar into tau. And remember, tau was that time, that average time which holds the Fermi sphere in its place because of scattering, different scattering process. You will recall those we covered in lecture number 3 or 4, something like that. We have written down this equation. That means k state will change for electron as we apply electric field. However, since bands are full, since bands are completely full, therefore, there is no space for electron to move. Since bands are full, there is no k state available for an electron to go into or move into, and therefore, this electron cannot move. An example will be, imagine a class, there are many chairs, these chairs are like energy states. Now, if all the chairs are occupied by the students come and sit in these chairs, and they are completely in there, sitting in the chairs. So, these are energy states in which now, and think of students as electrons, these students come and occupy the chairs, therefore, they are completely, the entire classroom is completely filled. that means there is no movement of students possible anymore. They are all, since all students are alike, we are thinking of electrons as indistinguishable particles. Therefore, even if you interchange two students, which we are assuming to be indistinguishable students, even if you interchange the two of them, the picture remains the same. It does not change. In a sense, nothing has changed even if you interchange two students, because they were indistinguishable students. Similarly, electrons are indistinguishable. So if they are on energy state, even if you interchange them, that does not make a difference. Just that effectively they have not moved. If the band is completely full of electrons, then it cannot change its K state, and therefore you can see that completely full bands cannot conduct. Filled bands cannot conduct. That is the second conclusion. First conclusion, second conclusion. What does that mean? At 0K, for the picture shown, what is that? Which picture we are talking about? This picture, the first picture right here, at 0K, in which band number 1 and 2 is completely full and band number 3 and 4 is completely empty. You cannot have conduction. You cannot have conduction because of that reason. That means that I am a picture of insulator. I have a picture of insulator which cannot be conducting at all. Except that now when we go to room temperature, some electrons, in this case I am talking about now this picture right here, the second picture, in which since the gap was not very large, this gap I am talking about, this particular gap was not very large, this point being this point and this point being this point, this gap not being too large, therefore in this schematic 3 electrons could jump to the next energy level. And notice that they jumped from top of the band below, band number 2, from top of the band into bottom of the third band, which was the lowest energy available. That is the minimum energy jump which is possible, and hence that is where the electrons would like to go. So since electrons would like to occupy the lowest energy, so from wherever they jump, the final picture will be like this, because in band 2 all the electrons would have taken the lowest energy, and the empty ones would be at empty K states would be right at the top. Whereas in case of band number 3, wherever they jumped, they will roll down to the lowest energy, and hence those 3 states which I am showing you will be filled, and if there are 3 electrons jumping, and others will be empty. If that is the case, clearly in this picture now, let us go to this picture at room temperature. At room temperature, so we talk at room temperature. Now our picture is band 1 is filled, completely filled, cannot conduct. That is a conclusion we already know. This cannot conduct and hence cannot contribute to current. Band number 4 is empty, is completely empty, cannot. You can see that band number 1 is completely full, band number 4 is completely empty. So therefore neither of these two bands can contribute to current at all. So cannot, instead of saying cannot conduct, I should really say cannot contribute to current. Cannot contribute to current. But now see, if you look at band number 2, band number 3 and band number 2, these band number 3 and band number 2, now you see they are partially filled. Band number 2 in this schematic has 3 empty states, and band number 3 has 3 electrons, and rest of the states are empty. So these bands now number 2 and 3 could possibly conduct, and when I have applied electric field, therefore you can see that K states begin to change, as I have shown you in the third picture. So what is this current is essentially that I want to show you that how does conduction happen in band number 2 and band number 3. So let's start looking at it. So let's say nearly empty band. Let's look at band number 3. its characteristic is nearly empty, but not completely empty. Band number 3 has some electrons. Band number 3 has some electrons right here, right here. In this case, or in this case right here, band number 3 now has some electrons. It's mostly empty, but it has few electrons. If that's the case, then what happens? In that case, if I write the current in band number 3 and I'll call it band number 3, if I think of a one dimensional example, let's say one dimensional, 1D dimensional solid is what we are talking about, let us say, whose length is L. L is the length of that solid. In that case, I'll write the current in through this band, because current contribution from band number 3 as being equal to minus Q being the charge. So, Q by L is the charge density, and summation of all the velocities where I is on the filled states, the states which are filled. The states which are filled, if I multiply by the velocity of those electrons, so there are 3 electrons I have shown, so the summation is over 3 electrons, the states on which it is filled, and then this will give you the current, which this will give you the current I3. So, it will start contributing to current. Now, this contributes to current. If I now look at band number 2, what is its characteristics? It's nearly full. If you look at this picture, you see green dots, which are green open circles, which are showing you the empty states, but other than that, it's almost completely full. So, therefore, it's nearly completely full. If I look at this particular band, then what the current will be? Same way, I can write this current I2 to be equal to minus Q as the charge divided by L gives me the charge density, linear charge density, multiplied by the velocities I, which is filled, I which is filled over filled states. Now, I can do a trick. Now, I can do trick. How many electrons are there? Recall that whatever is the number of primitive cells, in a material, that many K states are available in the first Brillouin zone. That was the consequence of Bloch's theorem, which I had taught to you. That whatever is the number of primitive cells, and if we are talking about only one atom in a primitive cell, if such is the case, in that case, then we will have whatever is the number of atoms, we will have that many number of K states in the first Brillouin zone. Since number of primitive cell in a material would be on order of Avogadro number, give and take one order magnitude, 10 to the power 23, 10 to the power 22 per centimeter cube is the density of atoms. Therefore, we know that if I take it 1 centimeter cube of material, I will have 10 to the power 22 or so primitive cells, and that many number of 10 to the power 22 number of filled states. If so, in order to compute this current I2, since this is nearly full, only few empty states, therefore, I must carry out this summation over all the filled state, almost Avogadro number of states. I must carry out this summation. I can play a trick. Recall that what is Vi? Wherever the electron is, Vi we have defined as 1 over h bar del E by del Ki. That is what we defined as the velocity of electron, if electron is occupying a state called Ki. If it is occupying, then that is the velocity. So, now if I carry out this summation, so now you look at the K states in a band number 2. If I have band number 2, this band number, and if I carry out this del E by del K type of summation on all these K states, whether they are occupied by electron or not occupied by electrons. So, then I am going to write this as del 1 over h bar. So, I am going to write this as 1 over h bar del E by del K Ki over all summation over all filled states or filled states, plus I will do this as summation over 1 over h del E by del Ki of over all the unfilled states or empty states, or let me call it empty states, then this quantity should be equal to 0. This quantity should be equal to 0. Why? Remember, what I am carrying out is essentially this is equal to, or I should write even one more step before I do this. I should write this as over all the K state in a band. In a band, this should be equal to 1 over h bar del E by del Ki, and that quantity should be equal to 0. Clearly, filled plus empty means all. So, if I look at band number 1, band number 2, then whatever are here are the filled state, the red dots, green open circles are unfilled, and then again red ones are filled states, and these are all the states. So, if I do a carry out this summation of del E by del K term over all these states, that means I am carrying over filled state plus unfilled state. But notice that for every K state here whose velocity I always have exactly negative velocity of that on the other side. If you wish, I will show you in this another picture here. Let us go back to this picture. If you will see that for every velocity here, I am showing you here, this portion here, whatever is the velocity, exactly symmetrical, because about k equal to 0, I will find a point where there is a negative velocity. If for every positive velocity here like this, I will have a negative velocity. For where the E versus K curve, since it is symmetric about k equal to 0, for every quantity del E by del Ki on one side, for the negative Ki for same value, same negative K value, I will have exactly same magnitude but a negative sign. And therefore, when I add up over all the states, I should have a picture where I would have a case where this over all the state, this whole thing will go to 0. If so, then what I can think of is, since remember this filled state is what I recall, I call them as Vi, and although it is not, the empty states are not filled with electrons, so I should not talk of electron velocity, but if I think of this quantity as velocity of some hypothetical particle, those green open circles which I have shown you, then I can think of this as empty, and I can write Vi of those particles, which I define as this basically in the same way. About this 1 by h del E by del Ki, I define then velocity of those hypothetical particles. Then I will say that this quantity is equal to 0. If so, I can now substitute this quantity in here. I can substitute in this quantity in here, and that I will do in the next page. So, I will write this I2 current, in which I will replace this I2 by this empty sites velocity, negative of that. So, I will write I2 as equal to minus Q by L. The way I have written is I filled Vi, but then I can write this same thing as plus Q by L I on empty states Vi. Now notice what have I achieved. What I have achieved is that instead of having to carry out the summation on Avogadro number of particles in band number 2, in band number 2, instead of carrying out summation over Avogadro number of particles because it is nearly full, I can get the same value of current by carrying out this summation over not the filled states, but over the empty states. I can carry out this summation over the empty states, except in that case I will have to change the sign of the charge. In that case I will have to change the sign of the charge, and also I will replace in future mass also by a positive quantity. In that case, what I define this hypothetical particle. So, if I carry out the summation over empty states, if I think of them to be occupying on a hypothetical particles which are empty states, in that case, in such cases like band 2, I can define a quantity called holes, which have now positive charge and also mass, which is effective mass, which is inverse, which is positive in this case. Now, this is the part, this is what introduces us to the idea of holes. Holes essentially, these are imaginary quantity, holes are imaginary quantities which help us in calculating the currents, which I would like to show you from this plot here. Recall that, now notice what happened. If you look at the solid curve, if you look at this solid curve E versus K, remember I was showing you in this case, I was showing you 3 dots here. Look at the effective mass here, look at the effective mass of solid lines. Effective mass here was negative, was a negative quantity. Wherever the slope of the curvature of E versus K curve is concave downwards, which is right here in this case, or in case of dotted lines it is right here, or in case of dotted lines right here, we find negative masses. In dotted lines right here we find negative effective mass. This negative effective mass can be treated as a positive quantity, we can convert it positive, and thought of to be occupied by a imaginary particle which has a positive charge, that is when it is empty, that is the empty places. So, remember, if electrons goes away, then where will holes like to live? Empty states would like to live, because since electrons would like to lower its energy, they will roll down to lowest possible energies. So, all the empty states would show up at the top of these bands. So, you can think of that whole energy is lowest at the top of the band, and hence they would like to reside where the curvatures are concave downwards. In such cases, effective mass of electron is a negative quantity, but you can think of effective mass of a hole therefore to be a positive quantity, and it carries a charge which is positive, and you make the charge to be positive because so that you can compute the current by carrying out addition only on the unfilled states rather than on the filled states. So, that is the basic idea of introduction of these holes. So, these holes are basically imaginary quantities where electrons are not, and the advantage you take is that instead of in band number 2, wherever you have fewer number of empty states, instead of carrying out summation over Avogadro number of filled states which are right here and here, you could carry out this summation only on the unfilled states and still get the same current I2. That is what I have proved to you, and hence defined electrons, and in process defined the idea of electrons and holes. All right, if that is the case, then let us go back to our this picture and see what happens. So, you are free to take a picture. So, now if I conclude all these together, empty bands do not contribute to total current. Filled bands do not contribute to total current, and total current of course in this picture is I1 plus I2 plus I3 plus I4 because of all 4 bands. Nearly empty band contribute to current, and what? Take the picture of electrons conducting. Take the picture of electrons conducting. Why? Because there are few electrons, nearly empty, there are few electrons. You have to carry out summation over few electrons only. In case of nearly filled bands contribute to current, but now you should take the picture of holes conducting. This way you will have to carry out summation over only fewer particles. The point being that whenever you see curvatures of this type concave downwards, it is worthwhile to think of holes conducting rather than electrons conducting. Wherever curvatures are concave upwards, in that case it is worthwhile taking picture of electrons conducting, because electrons will be sitting at the bottom of the band and only few of them are there. And therefore you can, so in other words, you can take a picture, so you can take a picture of in a band you can imagine electrons to be conducting or the holes, but not both. For example, in I2 band we took a picture of holes, in I3 for calculation of, in band number 3 for calculation of current I3 we took picture of electrons. So, but you cannot mix them up. Once you say band 3 you want to talk of electrons, then you have to stick to electrons only. When you want to talk in terms of holes, then you can talk in terms of holes for band 2. So, in a material for a particular band you can talk of electrons or holes, but not both in same band. That is basically the conclusion, and that now you can see why in semiconductors in valence band, what you call as valence band, you think in terms of holes, because there were very few of them. Otherwise valence band is full of electrons, and hence you speak in terms of holes. Whereas in conduction band you speak in terms of, in semiconductors you speak in terms of electrons, and that is because there are very few electrons. Rest of the states are empty like holes. You could in conduction band talk of holes because it is completely empty, but then you will have to carry out summation over Avogadro number of empty states. Similarly, in valence band you can speak in terms of electrons, but then you will have to carry out summation for currents over Avogadro number, and hence preference is for holes in valence band and electrons in conduction band. Holes you can now imagine is a mathematical quantity, a derived quantity, an absence of electrons where charge and effective masses are replaced according to the curvature of that particular band. So, that is where what I have introduced. In context of this, now we will have a brief comment on conductivity of materials. Okay, so now let us go further. So, I have shown you conductivity in relation to the band structure. So, what I will do is now make few comments on the conductivity of materials, and now we will try to complete the full circle and from where we started. Remember Drude's theory, etc., and we developed further ideas of conductivity, and now we are going to talk in terms of band diagrams in context of band structures. So, just brief comments, with some comments I will make briefly in next 5-10 minutes before I end this chapter and move on to the next module, where we will start talking about semiconductors in particular and the carrier densities. So, and optical properties of materials. So, what I am going to do is, before that I will make quick comments. So, let us start with alkali metals. Let us use a pen. Let us talk of alkali metals. Remember, these are the materials in which Drude's theory worked fairly well, and even free electron theory worked very well. And what are these materials? These are lithium, there are lithium, sodium and potassium and so on, many other. So, this is 1s2, 2s1, this is neon configuration, and then 3s1, and then this is argon configuration, and then 4s1 and so on. There are other cesium and other materials also in this. This is group 1a materials, and then we also have noble metals such as copper, which have one electron in the outer shell, like noble metals. You can talk of noble metals also, like gold, silver and copper. Also in this category, copper being of course equal to copper having argon configuration times 3d 10 and then 4s1. So, basically like potassium, except there are d electrons also involved in it. What happens? This is where Drude's theory and free electron theory worked well. What happened? Why did they work very well? Now remember, this structure of these particular these materials is BCC, BCC structure. If BCC is the structure, then the reciprocal lattice is like FCC. Reciprocal lattice is like FCC. And how many electrons per atom? There is only one outer shell electron is 1. So, there is one electron which is a conducting electron per atom. And if it is a BCC, and if I look at this now, number of K states that I will have therefore is equal to number of essentially number of primitive cell. Each primitive cell has one lattice point, and since this is a monovalent, in this particular case one lattice site is occupied by only one atom. That means number of atoms is same thing as number of primitive cells. So, whatever is the number of atoms, same is number of K states. So, if I have n atoms in this, then I have n number of K states in the first Brillouin zone alone. First Brillouin zone has n number of K states. Each K state can take 2 electrons. So, I can have 2n electrons filling the first Brillouin zone itself. And how many electrons do I have? If I have n atoms, each atom gives 1 electron. So, I have n electrons. What does that mean? First Brillouin zone could have taken 2n electrons, but I have n electrons. That means first Brillouin zone will be only half filled. That is what this means. So, if I look at this, then if I look at this, let me show you. If you look at this, since the structure is BCC, that means, what does that mean? That means the reciprocal lattice is like FCC. So, this is the reciprocal lattice for a BCC structure right here. Which is the shortest distance in this? The shortest distance in this is gamma to n. Gamma to n is the shortest distance, which is like saying this point from the center point right in the middle. Here is the point where intersection of this particular plane. In wherever the line being drawn to this particular lattice point, just messing up a little bit. So, let me draw it a little better. So, if you think of this particular plane, for example, and if you think of this particular as a lattice point here on this particular face, on this face is this center point on this face is this point. From the center of this zone, Brillouin zone shown, if you draw a line here, this red lines, the plane formed by red lines shows you a perpendicular bisector. So, that is what this point n is. That is the point this n is. So, what is the distance gamma to n? This distance of course is equal to 2 pi by a. 2 pi by a are these distances right here. Square root of 2 divided by 2 is the distance gamma to n. So, gamma to n. So, I will write this down here. So, this tau n is a distance which is 2 pi by a root 2 by 2, which is equal to about 2 pi by a in terms of 2 pi by a 0.707. Now, if I look at the Fermi sphere, then the radius of Fermi sphere in this case, if I think of Fermi surface to be spherical and I calculate for one, remember you can now calculate the radius of Fermi sphere, you have all the, we have done all the derivations. If you calculate this part, the radius of the Fermi sphere, then you will find that this quantity is 0.620 into 2 pi by a. Point being, this is smaller than the shortest distance in the Brillouin zone. That means, the Fermi sphere will be totally contained in the first Brillouin zone, and since you have only half filled Brillouin zone, so and it's in shape of Fermi sphere and partially filled band therefore. So, you have partially filled Brillouin zone and hence it can conduct. So, this material is a continuous band. First of all, it is a continuous band and it is partially filled. So, then partially filled band will conduct, and that is why you had this theory working, all these theories, free electron theories, because the surface itself is a sphere, since it can be contained fully within the Brillouin zone itself, and hence this theory, this alkali metals of group 1a, this theory, Root theory and free electron theory started working well. Some complications begin to show up when you go to copper. For example, if you go to copper, then instead of thinking of one conducting electron, there are places, if you are more interested, you can look at this electronic properties, the reference I have given you, electronic properties of materials by R.F. Hummel. So you can, there's a reference which has been given to you. You can use this reference, and there's a band diagram for there's a band diagram shown for copper, and you can read there. I'll state only in words because I want to be brief here. You will find that there are places where d electrons, d bands start coming very close to the s bands, and hence they interfere. They also play a part in conduction. So you might have to think in copper as if there are 11 electrons conducting rather than 1 electron conducting. But yet there are no band gap in this material, and this noble metals also conduct reasonably well. Now if we move on to next picture, which is group 2 divalent metals. If we move to divalent metals, example of this will be, for example, 2A metals, which are, let us say, beryllium. Let us take some examples: magnesium, calcium, strontium, etc., which is 1s2, 2s2, 3s2, argon, 4s2, and this is 5s2, 5s2. This is HCP structure, hexagonal close packed structure. This is hexagonal close packed structure. This is FCC, and this is also FCC structure. If I take group 2B metals, which have d electrons also in there, so zinc, for example, argon configuration, and then 3d10 and 4s2, or I take cadmium or mercury, where we talk of xenon here, and this is 4d10, 5s2, this is 4f14, 5d10 and 6s2 is this configuration. Let us look at them one by one. Now what happens here? What happens here? Why do these metals conduct? Notice this, now we have 2 electrons. So if we think of FCC, number of atoms same as primitive cell. If we have 1 atom on each lattice point, then number of primitive cells same as number of atoms. If that is the case, then first Brillouin zone will be able to accommodate, if there are n atoms, in that case I will have n k states. Again I repeat the story, each k state can take 2 electrons, spin up and spin down. Therefore it can take 2n electrons. And how many electrons are there in first Brillouin zone? Now in this case, per atom there are 2 electrons which are going to conduct. So if there are n atoms, then I will have 2n electrons. So 2n states in first Brillouin zone and 2n electrons in first Brillouin zone. What does that mean? The first Brillouin zone would be completely full, and hence we must think of these as insulators. But your experience tells you that no, these materials, magnesium, calcium, etc., are conductors. So what is happening? What is happening is this, that since there are continuous band, there are no band gaps. So therefore take example of, for example, you take example of this magnesium. In this case what you find is that you have 2p band, you have, this is 3s band, this is the 3s band, which should have been completely full with 2 electrons, but there is a partially overlapping next higher band, 3p band, which is next higher band up there, which is now also there. So there is a 3p band right here in magnesium, for example, overlapping. So what happens is, the picture is that result of this is that some of these electrons, I draw a picture a little better, some of these electrons can flow over into this band, also 3p band also, and hence 3s band is partially empty, as is 3p band, which has only few electrons. Consequence of that is that this also becomes a partially filled band, and hence this can conduct, though its conductivity is slightly lower than normal metals we talk about. In group 2b metals, again 4d electrons, these d electrons also playing a part, but in case of zinc and cadmium, the d electrons are far below the 4s band. And if you look at the band diagram, 4s of s bands, and hence d electrons do not play too much of a part. In mercury Indeed, however, d bands are fairly close to the s bands, sometimes they intersect. Therefore, you must think of s and d electrons together in case of mercury. But the point is that again in these cases, because they are continuous band, there is no band gap, these materials are still conducting. Which brings to me to the point where you can recall I had written sigma as conductivity as equal to, after free electron theory, I had derived that conductivity in context of free electron theory to be approximately 1 over q square charge square times Fermi velocity square times some tau, and I had written density of states, which are occupied actually, but nonetheless density of states also had included. This is, notice this density of states. I could think of this therefore something like this. I could think of density of states like this in the energy scale. Remember, if I think of a band, what does that mean? If I think of a band, I mean that below it there are no energy states, there are energy states not allowed, energy states above it are not allowed. That means those are disallowed energy states. That means density of energy states there is nearly 0. So, somewhere here is 0 at the top of the band, at the bottom of the band the energy states are 0. So, if I plot this density of states, it shows a maximum somewhere here in the middle shows the maximum. And what happens? In case of monovalent metals, the Fermi energy lies somewhere here, EF for a Fermi energy for monovalent metals, because for example alkali metals of group 1a, where we have only one electron, the half filled bands are half filled. Since they are half filled, so they are somewhere in the middle where the density of state is maximum. This G is maximum therefore, and hence conductivity is very high. In case of bivalent metal, we can think of, if I take a picture of 3BP band, if I think of this as 3p band, then I will think of Fermi energy to be somewhere here. Here is the Fermi energy. So, I will show that Fermi energy somewhere here as energy for a bivalent metal. In that case, I do have some G, I have some G here, some value of density of states, and hence I have some conductivity, but not as good as monovalent metals. If I think of now bands which are completely full, in that case Fermi energy somewhere in the top, and I would think of that for such materials EI to be the Fermi energy, where density of states is nearly 0, and hence I would think of again conductivity to be very, very poor in those materials. Let us call them insulator. Therefore, I have written the subscript I for those cases. So, we can take such a picture, show this picture, and from what we have derived for free electron theory, from that formula we can think of conductivity, why there are differences in conductivity in this way. Briefly, I will also mention trivalent metal, because that was a problem which we never were able to resolve. You will recall in case of aluminum, where we think of 3 electrons conducting in free electron theory or Drude theory, we found the Hall coefficient to be equal to Hall coefficient came multiplied by n times q came out, or rather I should write this in different form, RH which was measured and RH which was theoretically predicted,